started.
Okay, part 2. Let's do some polar calculus now. You can hopefully just print up this little piece of paper, or if you haven't, if you're not watching the video today, you can grab one of these from me on Thursday or Friday or something. So we're going to do a little...
You want to close up so we can see what paper you're talking about?
You'll get, I'll email it out, but it should look something like this. Basically has these things on here. So I want to find the slope of a line tangent to a polar curve. There's just some arbitrary curve drawn on there with no real particular significance, and then just some arbitrary tangent line. So I want the slope, which kind of has not a whole lot to do with r or theta. It's still dy dx, it's still the change in y over the change in x. So I need a way to express the change in y. I just need some way to relate sort of y and x here. So what's hopefully not too crazy is dy dx is just going to be dy d theta over dx d theta. Just hopefully that's fine and everybody's on board. I just need a way to express x in terms of theta and also to express y in terms of theta, which I have because just x equals r cosine theta and y equals r sine theta. So all that stuff is pretty much just here, and I'm going to have some equation, r equals, I don't care, we can call it f of theta if you want, or we could even just call it r equals something like 2 cosine theta plus 2 or something like that. But this would just be some function. But for now, let's just do it generically for any r equals equation. So if y is equal to r sine theta, then dy d theta is just the derivative of r, which we would just call dr d theta, leave the sine, plus, now leave the r, and then the derivative of sine is cosine. And then I also need the derivative of x with respect to theta. So if x is r cosine theta, then dx d theta is just derivative of r, which is dr d theta, leave the cosine, product rule, so split that up with a plus, leave the r, derivative of cosine is just negative sine. So aka dr d theta cosine theta minus r sine theta. So I really just need to put one of them on top of the other one, and then I'm kind of done. So let's just put that one on top of, or sorry, the y one on top of the x one, and then we're pretty much good. So we get r cosine theta plus dr d theta sine theta over that thing, which is dr d theta cosine theta minus r sine theta. That's pretty much it. Now you can memorize this as a formula if you really, really want to. I highly discourage you from doing that. And I kind of switched the order of these for really no particular reason, because hopefully, well, I guess there is a reason. You know this. Hopefully, you know that sine alpha, you know the sum and difference formulas for these. That this is sine alpha cosine beta plus or minus cosine alpha sine beta. And this is cosine alpha cosine beta minus plus sine alpha sine beta. You hopefully know your sum and difference identities. That the sine one goes sine, cosine, cosine, sine, and the cosine one goes cosine, cosine, sine, 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 aka switch the middle sign. I'm really only saying this because Mr. Stein likes to yell another little crazy thing here, where he'll just say generic polar derivative is r cosine dr cosine sine r sine. Just switch this sign from a plus to a minus.
It's terrible.
Yes. Seriously, just do them independently. You know x is r cosine theta, you know y is r sine theta. Just put one on top of the other. But you should know these things. They're very, very helpful. And will be helpful to some extent on what we're doing with the next one. So we're just going to look at a specific example where we do a little polar calculus and find some tangent lines. So if you already printed this sheet or have it, if you could just flip it over, and we're going to talk about a specific graph, r equals 2 minus 2 cosine theta.
Which Which is that graph, right?
Basically is that graph. But we'll graph it kind of generically, and then we'll talk from there. So we want r equals 2 minus 2 cosine theta. Your graph is blank. The graph should wind up looking similar to the graph we did before. But if we draw our standard auxiliary graph, cosine starts at the cosine starts at the max, but we're flipped over. So we should be here, then here, then here, then here, then here. And we should look like this. That's pi, that's 2 pi. We get something like that. So I should be able to use this on some sort of polar graph. To my advantage. This thing should be, when theta is 0, r is 2. Or sorry, when theta is 0, r is 0. When theta is pi over 2, r is 2. So that whole time, as theta gets bigger, r just gets bigger and bigger and bigger. R just keeps getting bigger and bigger until at pi we're 4 units away. So we look something like this. Then we get smaller and smaller and smaller until at 3 pi over 2 we're 2 units away. Then we keep getting closer and closer and closer until we're 0 units away. That's it. In case you don't know this already, when it's in the form a plus a cosine theta, this thing is called a cardioid. It's really just a special case of a Lima sign. No vocab quiz planned on the names of polar curves. But that's pretty much it. So we want to find the slopes or the location of any vertical and horizontal tangent lines. So we need to find dy dx. So let's start by talking about y, which is r sine theta, and x, which is r cosine theta. There's no real particular rhyme or reason when I have y first and x second, but you're going to need to put this one on top of this one to talk about dy dx. So y is really r sine theta, but we actually know what r is in this case. This is a specific value for r, so this is 2 minus 2 cosine theta times sine theta. And x is the same thing, 2 minus 2 cosine theta times cosine theta. And then we just have to do it. And whatever we get, we get. So dy d theta should be the derivative of this. Maybe you want to distribute before you take the derivative. Maybe you don't. I don't really know. It's kind of a personal preference thing. But the derivative of 2 minus 2 cosine theta, that's just 0. The derivative of cosine is going to be negative sine. So this is just going to be 2 sine theta, the negative canceling out this. Leave the sine, plus leave the 2 minus 2 cosine theta, and then the derivative of sine is just cosine, which maybe you like better as 2 sine squared theta. This is going to be plus 2 cosine theta minus 2 cosine squared theta. And that's kind of okay, although we might want to simplify that a touch. Here, kind of the same thing. Dx d theta is just going to be the derivative of 2 minus 2 cosine theta, which is going to be the same thing we got here. It's going to be 2 sine theta again, this time times cosine theta. Plus, now we'll leave the 2 minus 2 cosine theta, and we'll take the derivative of cosine, which is just negative sine. So we eventually wind up with dx d theta is equal to 2 sine theta cosine theta minus 2 sine theta plus 2 sine theta cosine theta, or dx d theta is 4 sine theta cosine theta minus 2 sine theta. But I say we can make these things look a little prettier. If we go back to our sine alpha plus beta, aka sine cosine plus cosine sine, be a beta. If we just think of these two angles as being the same, you get sine theta, cosine theta, plus cosine theta, sine theta, aka 2 sine theta, cosine theta. We have one of our double angle identities just sitting right here, just kind of in reverse. You've got the right side, you've got a sine times cosine, as opposed to, you don't see a sine 2 theta, we're going to see something like this and turn it back into something like this. So that should eventually give us that, our nicest version of dx d theta is, we have 4 sine cosine, so that should be 2 times 2 sine cosine, aka 2 of those, just 2 of those. We should have 2 sine 2 theta. And then we still have this minus 2 sine theta. That's probably our nicest version of dx d theta. Whereas dy d theta, we have this other sort of thing. You go back to your cosine theta plus theta. That should be cosine, cosine, sine, 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 aka cosine squared minus sine squared. That's cosine 2 theta. And we basically have that here, except we have the sine squareds minus the cosine squareds instead of the cosine squareds minus the sine squareds. All I'm doing is subtracting in the opposite order. So this minus this should be negative cosine 2 theta. Well, really negative 2 cosine 2 theta. So dy d theta in its nicest form is probably negative 2 cosine 2 theta plus 2 cosine theta. So now if I want dr d theta, I just need to take dy d theta divided by dx d theta, and I just get 2 cosine theta minus 2 cosine 2 theta over 2 sine 2 theta minus 2 sine theta, which is probably better if I just cut everything in half and just call this cosine theta minus cosine of 2 theta over sine of 2 theta minus sine of theta. It's probably our nicest derivative.
All right.
Nice. So, derivative successfully found. Now we should be able.
What was the point of simplifying all that stuff? Just because?
It looks nicer and prettier. It's not really wrong if you took that, or sorry, that and put it on top of that. This is maybe nicer. We're going to actually do something with our derivative, so simplifying it might actually, and at least is helpful in one of the 2 cases. So the other thing we wanted is horizontal and vertical tangent lines. So let's hunt for some horizontal ones first. So that just should mean dy dx is 0, which means its numerator is 0. So we should just be saying cosine of theta minus cosine of 2 theta is equal to 0. And we can kind of tell where they're going to be. You can kind of just see they're going to be there. And maybe even one here, right at the pole, right where it kind of dimples in. So we should just be able to solve this equation. So we could do that. We could do that. So it's kind of some bad algebra. Just because cosine of theta is equal to cosine of 2 theta doesn't mean these 2 things have to be exactly the same thing. Cosine of 2 pi is equal to, or cosine of 4 pi, that's true. Cosine of 2 pi over 3 is equal to cosine of 4 pi over 3. They're both negative a half. And you wind up kind of losing solutions. Cosine is not a one-to-one function, so this is kind of trash algebra. So what we want to do instead is the one trig identity that it's impossible for anybody to not know is that 1 is sine squared x plus cosine squared x. So if that's true, then the sine squared here in our double angle identity for cosine should just be cosine squared theta minus sine squared would just be 1 minus cosine squared. So this is cosine squared minus 1 minus cosine squared, aka 2 cosine squared theta minus 1. So you'd rather just replace this cosine 2 theta with 2 cosine squared theta minus 1. Just watch your parentheses and you're okay. You've also got a third alternate double angle cosine identity. And if 1 equals sine squared plus cosine squared, we could replace the sine squareds with 1 minus cosine squareds, or you could replace the cosine squareds with 1 minus sine squareds, in which case you'd get 1 minus sine squared theta minus sine squared theta, aka 1 minus 2 sine squared theta. So now this is like completely and totally solvable. This is negative 2 cosine squared theta plus 1 plus cosine theta for 2 cosine squared theta plus, minus cosine theta minus 1. And you just multiply both sides by negative 1, or flip the signs, or divide both sides by negative 1, whatever. It's all the same thing. So let's factor this. Definitely 1 and 1. I want this one to be negative and this one to be positive. So cosine theta equals a half negative, or cosine theta equals 1. So here, you know when cosine is negative a half. That happens here or here. That's 2 pi over 3 or 4 pi over 3. But be careful, there are like infinity other angles that work here too. We're talking 2 pi over 3 plus 2 pi k, or 4 pi over 3 plus 2 pi k. You know when cosine is 1. That happens right here. That's just theta is 0 plus 2 pi k. Obviously the 0 is kind of silly. But be careful about just writing arc cosine of negative a half. That's just one value. There are 2 places where, 2 locations where cosine is this thing. For our purposes, we kind of only care about 2 pi over 3, 4 pi over 3, and 0, because this thing just loops around and just keeps making the same cardioid over and over and over again. So we know that theta is 2 pi over 3. Or theta is 4 pi over 3, or theta is 0. Which kind of looks like it fits on our graph. That looks like that's probably 2 pi over 3, that's probably 0, and that's probably 4 pi over 3. Seems to make sense. All the r's we already know are positive, so that seems to make totally logical sense. Second quadrant angles are actually going to graph in the second quadrant because the r's are positive. So if we're just looking for the equation of horizontal lines, we kind of only care about the y coordinate. I don't need to find the x coordinate. That's going to tell me where it's actually tangent to the curve. But I just need the y equation. This is just like y equals 3 or something like that. So let's just find y. So y should just be, since y is r sine theta, aka 2 minus 2 cosine theta times sine theta, y is just 2 minus 2 sine 2 pi over 3 times sine of 2 pi over 3. Sine of 2 pi over 3 is root 3 over 2. Root 3 over 2 doubled is root 3. So this is 2 minus root 3. Times sine of 2 pi over 3 is also going to be root 3 over 2. So if I distribute that root 3 over 2, y equals root 3 minus 3 halves.
Yeah.
So root 3 is like 1.7. Wait, did I mess that up somewhere? This should be.
Oh yeah. When you plugged into R, you should use cosine, not sine.
Oh, I just wrote a sine here. This
Yeah.
should be a cosine.
Sorry, I didn't catch that.
That's okay. So cosine of 2 pi over 3 is actually negative a half.
Yeah.
So this is negative 2 times negative a half, which is going to turn into plus 1. So we just get 3 root 3 over 2, which just should be this one.
Nice job of checking your answer to see if it's reasonable, Giles, and realizing that something was wrong, and therefore going back and finding your mistake.
Yay. Thank you, Mr. Rose. The tangent line just seemed totally unreasonable. So this is y equals 3 root 3 over 2. We can do the same thing with 4 pi over 3. Well, 4 pi over 3 has the same cosine, so this thing's going to work out exactly the same thing. Its sign is just negative.
Kind of boring, yeah.
So this is just going to wind up being 2 plus 1 times negative root 3 over 2, or negative y equals negative 3 root 3 over 2. Which kind of makes sense just because you know this curve is actually symmetric. So you can kind of just tell that the amount this one is down is the same amount this one is up. We also need that one at 0, so let's just plug it in.
Before you move on, maybe it's worth mentioning, like, when theta is 2 pi over 3, r is 4? No. I messed up. What's r?
R is going to be
3. So it's just kind of a cool thing that you could never do before without calculus. Like, we know just like that polar point, that's like the polar point 3 comma 2 pi over 3.
Yeah,
that might help.
3 comma 2 pi over 3.
That's like where the cardioid has its horizontal tangent.
Same thing here. This guy is just going to be 3 comma 4 pi over 3. You can just plug in 2 pi over 3 and 4 pi over 3 to check those. Same thing with theta equals 0. We just plug it in. 2 minus 2 cosine of 0. Well, cosine of 0 is 1. That's why we listed it as one of the things that made cosine 1. So this should be y equals 2 minus 1 times the sine of theta, which is 0. So y equals 0, which kind of makes sense with our picture too, that this tangent line at this kind of cusp is y equals 0, that a horizontal line best represents the curve. And then we basically just do the same thing for vertical tangent lines. If you want a vertical tangent line, dy dx would be undefined or not exist. And that means the denominator, aka dx d theta, has to be 0.
You can kind of guess one of the answers right away, like at pi.
That's a good point. I agree with Mr. Rose. It kind of looks like we have one here, and we have one here. But it looks like this vertical tangent line is tangent at 2 different locations. But in terms of where are vertical tangent lines, they're at 2 different places. What is that tangent line? It's the same one. So you kind of have to be careful about, I guess, how the question is phrased. If it wants the points where it's tangent at, there it looks like there's 1, 2, 3 of them. If it's talking about how many tangent lines are there, or what are those lines, there are only 1, 2 of them. So here, let's just set dx d theta equal to 0, which is just 2, is just that, except we already divided by 2's. So we can just say sine of 2 theta minus sine theta equals 0. This is probably one of the cases where it didn't work out quite so pretty, that using the trig identity was not helpful. When we did the cosine one, we applied this double angle identity to make it look nicer and prettier. But then that wound up being not so helpful. We wound up applying one of the different double angle identities from there. Here, if we just left this thing originally like that, we'd kind of be okay, because I now want to just sort of reapply the double angle identity and kind of take it actually back to where we started almost. That this is 2 sine theta cosine theta minus sine theta equals 0. This one's super easy factoring. Let's just pull out a sine theta. We're leaving behind 2 cosine theta minus 1. So when is sine theta equal 0, or when is cosine theta equal to a half? You know where sine is 0. That's here and here. That's theta equals 0 plus 2 pi k, but kind of the same deal. We kind of only care about the 0. Pi plus 2 pi k, we kind of only care about the pi. I don't know why I didn't just write the answers as pi plus pi k, or pi k for that matter. It's all multiples of pi. 0, pi, 2 pi, 3 pi, 4 pi. When it's cosine a half, you know those ones as well. Pi over 3 and 5 pi over 3. Some people would call that spot negative pi over 3, but we kind of never graphed that. When we graphed our original cardioid, we only graphed angles from 0 to 2 pi, so I would call this position 5 pi over 3 instead. So finding horizontal and vertical tangent lines should be nice, because one coordinate is constant. In this case, for vertical tangent lines, we only care about their x coordinate. So let's just find x, and x is r cosine theta. X should just be, when theta is pi, x should just be 2 minus 2 cosine pi. Times cosine of pi. So cosine of pi is negative 1. That's going to make this a 4. Cosine of pi is negative 1, again. That's going to make this x equals negative 4. And that's the one you could kind of tell before you even did anything. You were fairly confident, like 99.9% confident that it was going to happen right there. What's weird, I guess, is the theta equals 0.
That is weird.
Because that was a place where we also had a vertical, or we had a horizontal tangent line. And you can tell, seriously, look at this position. A vertical tangent line is not the line that best approximates the curve at this particular place. It's a horizontal tangent line. So you kind of have to be careful about things that make your numerator 0 and also your denominator 0. The only way to do those is basically graphically. And you can just tell that that happens, that's a horizontal tangent line, not a vertical tangent line. So graphically is helpful. This winds up being garbage. Here, at pi over 3, it should be 2 minus 2 cosine theta. So that's 2 minus 2 times a half, since the cosine is a half. Then times a half. That's just going to be 2 minus 1. That's just 1. That's just going to be x equals a half. And this angle, 5 pi over 3, has the same x-coordinate because it has the same cosine, and only cosines are involved in making x, at least in our setup here for this particular curve. So x equals a half is going to happen to be the tangent line at two different places, at this one and this one. Pictures are helpful. Draw them. You should know your trig identities. If not, you should be able to derive the doubles. They're super easy, assuming you know sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. But know your doubles. They're very, very helpful. They come up a lot in polar, especially with all the roses and things like that. So that's it.
You can also, again, you can plug the point in, right? Like when theta is pi over 3, r is 1.
Yeah, this is going to be 1. When theta is pi over 3, that's going to be 2 minus 2 times a half, which is 1. Which doesn't show quite super perfectly on our graph, but I kind of have a not the world's greatest scale. Just drew a bunch of rings. So hopefully this is a good thing, and we won't have to frantically cram, and you'll all get 5s on your AP test. It'll be great. Cool.
Done?
Done.